Okay, so the Archimedes principle is about how buoyant force produce the force against that the object submerged into the fluid. So if usually the rule of thumb is you have the some kind of object, put it inside the fluid, and depending on the relative density of the object to the surrounding fluid, it could have negative buoyant force or positive buoyant force. So if density is higher than the surrounding liquid or fluid, then the object itself should experience the negative buoyant force. If density of the object has less density than the surrounding fluid, then that object should have positive buoyant force, which is upward in the vertical direction. So let me show you the simple picture describe that Archimedes principle. So basically, let me just write Archimedes principle. Now you have some amount of fluid contained in maybe cylinder or some kind of container, and that fluid has some density, maybe a low F. And now if you have some object with arbitrary shape, and once it's fully submerged into or partially submerged into this fluid, then this object will experience some pressure or force around the objects from the surrounding fluid. So obviously that produced the buoyant force upward. At the same time, the object itself creates gravity, the downward force. Oops, what? Hold on. Let me, there's some kind of issue with my pen. So, let me, okay. So the downward force is gravity. So when this gravity and buoyant force stay in balance, then object will be floating inside of this fluid. But the buoyant force is bigger than gravity, then obviously this object will have the positive force upwards due to the buoyant force. So Archimedes principle is, now if you have like a uniform fluid that completely fill this container, then this the force inside the fluid, there's no discontinuity. But if you have some sort of object with a different density than the fluid, the density mu law, then the amount of force, net force exerted on this object is same as the volume has been displaced by the body. So now you have this amount of the volume out of the object, then if the density itself is same as, obviously there's no object submerged into this fluid yet. So there's no net force because the buoyant force upward and the gravity is perfectly balanced because the density between the inside of this boundary and outside of the boundary is just same. But if you replace that boundary inside the boundary with the different object, different material, then density will be different. Then that amount of difference between the material inside the boundary and the density of the surrounding fluid producing net force either upward and downward. That is called the Archimedes principle. So when a body is fully or partially submerged in a fluid, a buoyant force from the surrounding fluid acts on the body. So the force is directed upward, could be the downward if it's negative value, and has magnitude equal to the weight, the weight of the fluid that has been displaced by the body. So this body itself now just occupy the same volume that this liquid or fluid actually supposed occupy, suppose occupy, right? But if you, because of the difference between the density, that this object will experience amount of force produced by the surrounding fluid that makes the buoyant force. So now we have this amount of volume with the fluid and same amount, same volume, same shape, but with a different object, with a different density. So the amount of force this object experience is same as this liquid or the fluid actually produce in the condition that fluid actually create the buoyant force upward. Okay, so now let's just set up to some specific condition. Now you have some kind of box partially submerged into some fluid. So if you're standing in boundary between this object or surface of this fluid, then that object will experience buoyant force upward, and then gravity downward. So the buoyant force is density of fluid times volume of this plate G. So this one is M F. That's the amount of of volume displayed by the body. And now you have gravity, which is low times volume V naught times G. So this very specific example to actually well explain the Archimedes principle, because now you have the total volume of this object subject to the gravity, which is mg. Then that could be expressed with the low naught, which is density of this object times volume of this whole object times gravitational constant value g. That actually, so that m is same as low naught times v naught. That amount of gravity should be same as this buoyant force. The fluid of F times displaced volume by this fluid times G. So when this buoyant force stay in balance, this body, this object can be floating over the surface. What if this gravity is bigger than the buoyant force?
Then it'll sink.
Yes, it will sink. Then what circumstance make the buoyant force or gravity is bigger than buoyant force?
If the box has a greater density than the fluid?
Yes, that's the rule of thumb. That's just obviously if you have not only but only density, also volume related. So if you have some sort of density, then it's just multiplied by the displaced volume. That amount of effective mass is bigger than the gravity, the mass part of the gravity, then make object floating over the surface. So you can actually make a critical condition that indicate the buoyant force is same as gravity. So FB, buoyant force, mg, so that's low fluid density times displaced volume times gravitational constant g is same as low v not g, then that make this under this condition that object of body can float on the surface or stay in the same spot inside of the fluid. So now you have same g from the both sides. So that provide the ratio between the displaced volume and the total volume of object and the density ratio. So that should be volume displaced over total volume of body equals low naught or low F. So if you know the actually density density of the object and density of fluid, and you can find the ratio of the displaced volume and the total volume. So if you know the amount of volume of the object, you can estimate how much volume actually displaced by estimate this density ratio, right? So an object on a fluid, if its density low, is less than that of the fluid, right? So from that, there's two different weight in a fluid. So one is the real actual weight, the other one is parent weight. So if from this configuration, you can define the two different actually weight in terms of how they actually appeared in the surrounding fluid. So the apparent weight in a fluid defined by this definition. So apparent weight W apparent is actual weight W minus magnitude of buoyant force FB. So this equation just shows that if there's a large amount of difference between the two different material, the object of your interest and the surrounding fluid in density, then the difference of the weight between apparent weight and actual weight is larger. Okay, density difference is bigger and bigger than the weight difference between apparent weight and actual weight becomes also bigger. So this is the summarized notation of the Archimedes principle. So if you want to know that the objects density of the objects of interest is the pure, or it has some sort of alloy or some sort of contaminant, then you can actually put it into some fluid that you already know its density. Then you can actually figure out the percentage of purity of the object. So we will have chance to solve the problem using this Archimedes principle later on. But you got to make sure this the apparent weight, which is the weight only appeared the out of the fluid is same as the actual weight measured by the scale minus actually a magnitude of buoyant force. The buoyant force make these two weight look different. Okay, so the amount of difference depend on the density between the fluiding and the surrounding fluid and the object of your interest. Okay,
Mhm.
so that is Archimedes the principle. And before moving on to the Bernoulli's equation, we will have to actually also take a look at the two different fluid in their definitions. Usually, real world, all the fluid, they do not behave like ideal fluid described in this theoretical model. So in order to actually simplify the condition, and also in order to make some principal model of fluidic dynamics, you have to set up the ideal condition for fluid. So the ideal fluid, they have different characteristic, the one in the real practical actually condition. So that ideal fluid, there's few conditions to justify the ideal fluid in nature, especially in the way to describe that model of fluid dynamics. Real fluidic motion is very complicating. There's a lot of actually nonlinearity and a lot of complexity involved in the way of describing the fluidic dynamics, especially if the fluid actually goes through the complex shape of the path of motion. So if you have for example, if you look at like the floor of a lever, there's all kinds of complexity added into the emotion. So there's absolutely no way to describe the lever floor with a one single principle or theory. So in order to actually create or describe the motion of fluid, you have to first assume that some kind of preconditions, the way to describe the fluid or liquid. So there are few constraints of ideal fluid. I will just list some of them. So so real fluid motion is very, very complicated. There's non-linearity and chaos. It's like all kind of crazy things are just involved in the way of the fluidic dynamics in a real circumstance. So because of that, even nowadays, modern times, they're not fully actually understood. Okay, there's just like their complexity is unsolvable by a simple model. So we have to set up the ideal fluid to simplify the case of dynamics. It's simpler to handle, so you can actually easily describe their motion. So number one, many cases we only just take a look at the steady flow, which is the laminar flow. So the velocity of the moving fluid at any fixed point does not change with time. So basically, we consider the certain condition that velocity of the fluid moving with the constant velocity, which means instantaneous velocity of the fluid is same as average velocity at certain point. So that make problem is much simpler. So we don't want to just take a look at the localized velocity element in their volume. Number two, incompressible Oh, sorry, incompressible supple floor. What do you think this word means?
Um, like you can't compress it into like a solid.
So okay, that's right way to describe this word. But what does it mean in physics?
It's always changing.
No, it's not always. Is always unchanging actually. So no, let's assume that you have the floor along the path of the fluid actually moving along this some kind of pipe. While you there's fluid moving in the given area or given length of our interest, at least the pressure is constant and their density inside of this given area of our interest must be constant too, which means their density in the local area should not be different from that average density over given space. That means the space between the molecules inside of this fluid should not change in time. If their separation between the molecules inside of this fluid change in time in local area, that means your density is fluctuated and some area of this fluid should have higher density than average, right? Than or lower than average, then this volume of this object, I mean, this fluid will be also changed, which means that fluid will be compressed or decompressed over time. So that adds one more complexity in your theoretical model. So that density itself is time dependent, and that means it's really complex to analyze that dynamics of fluid. So a simple model, just like Archimedes principle or Bernoulli equations, any type of simple model of fluidic dynamics, normally based on incompressible nature of fluor, which means the density and volume and time, I mean, the pressure is just constant value over some time. So that is actually connected to the first condition, steady flow, laminar flow. Okay. So realistic, actually fluidic dynamics only can be solved by the numerical approach, which means you have to use a computer because that density normally just change in time. But in that case, you'll not be able to solve that problem by your two hands. It's way too complex. So in order to use that, the idea of the simple model that fluid itself should be assumed to be the incompressible, all right? And number three, then there should be non-viscous fluor. So that means because of the molecular dynamics inside the fluid, there should not be the viscosity, just dragging force, creating the force which actually drag the fluid. So once when they actually the fluid actually travel from one spot to the other, then the viscosity should not change their velocity. Okay. So that means if you have viscosity come to play, then the velocity will change over time. In that case, the first condition, steady flow, will not be no longer valid. You can't just apply the steady flow. So viscosity should not be involved in your way of described in a fluidic motion. So number 4, irrotational flow. So this is regarding the direction of flow rather than the scale of quantity like density or volume. So for example, if the fluid have rotational motion inside the circular the tube, like this kind of tube, we only consider that the fluid also only has one cycle of one directional motion. If you allow this fluid have like a rotational motion, local space, then you also have like this kind of motion, like this kind of motion, right? Cycling motion around this fluid. That is create a turbulence, turbulence inside of the like travel path, and that is way more complicating dynamics. Uh, that is not be easily solved by the the theoretical model. So we only assume that 1 degree of first order of first degree of like a motion, like a one directional motion of fluid. So if you have pipe, that water or any type of fluid or liquid travel in the one linear motion, one direction. There's no kind of like a local motion added into this description of fluid. Okay, so that make this any type of dynamics much simpler, and your job is much easier to solve. All right. So there are 4 different conditions. Number 1, steady flow, laminar flow, incompressible flow, and the non-viscous flow, and the irrotational flow must be assumed before you actually just set up the model to solve the problem. Okay. So under this constraint, you can actually set up the continuity or equation of continuity or continuity equation. Let me move on to that part. So in order to describe that the static motion of the fluid dynamics, you have to use that the 4 different constraints, and that 4 different constraints make your fluidic dynamics much simpler and valid too. Now you assume that simple case of example. So now the water pipe, it could be like an oil pipe, any type of pipe or tube with some kind of fluid just runs from one point to the other. So that size of the pipe varies along the travel distance. So you have the pipe with one side area A1 with the larger size the pipe than the other. So that is A2. So that is A2. And this one is A1. The input of this pipe is A1, has the area of A1. Output of outlet of this pipe has the A2 of area. So while this fluid moving from the one side, the one point to the other in one side of this pipe, which is travel distance delta L1, then that fluid move with the V1 on the input of this pipe, then output of this pipe, that fluid actually change their speed because the size of pipe is narrower. So that should create a different amount of speed of fluid at output or outlet of this pipe, and the travel distance with a different speed is the delta L2. So under this condition, mass flow rate could be defined by this definition. Mass flow rate is just the change of the mass in time, in given time. So that is delta m over delta t. So again, the mass flow rate is how fast mass change in given time of fluid of your interest. So staying with that definition, delta m1, the mass variation of input side of this pipe is given by delta m1 over delta t. The time delta t is travel time of this amount of cylindrical volume of fluid, and that is mass. The density of this fluid in the entrance of this pipe is low 1 times delta V1. Okay, here, I mean, that is the volume. I mean, so delta V1 is actually volume of this cylinder of entrance. And now this volume, the volume variation in input should be expressed with the area A1 times travel distance L1, right? Divided by delta T. So the low one, the density of fluid in that area, input or inlet of this pipe is constant value. A1 is constant value, so that could be out of the delta. So that should be low 1 times A1 times delta L1 over delta T. So this is the velocity V1, right? So that mass flow rate could be expressed with the low 1, A1, and V1. So combination of density, area, and velocity. Same thing, the mass flow rate output of this pipe should be delta M2 over delta T. By means of the same derivation, like input flow rate, you can just get this result, low 2, A2, V2. You understand this, right? Just like same way to just, drive this formula. But mass flow rate must be same for input and output or inlet and outlet. So from that, low 1, A1 times B1 must be same as low 2, A2, B2. So basically, how fast the mass change in input side is same as the one in output side. So if you have put like a 10-gallon with some amount of speed in the input, then same amount of mass should be coming out of the output or outlet at the same time. Okay, so that is the conserved actually quantity. So from that, you see that, as I said, this fluid is incompressible fluid, right? So low one must be same as what? Lowest density.
Um,
Low one should be same as what? Low two, I just made the assumption that the low one and the low two are different, but based on the ideal floor, you remember that floor itself should be the incompressible. That means what? Low one should be what does the compressible incompressible means?
Like the space between the fluid molecules don't change.
Yeah, that same as the what physical quantity is conserved.
Volume?
No, volume change, but between the space between the molecules just stays same, then the space determine that how many molecules stay in the given volume, which means density. So density must be same. So low one should be same as low two. That is condition for incompressible. Okay, so we can take a low one, low two out of this formula because they are same. So area times velocity of fluor or fluid should be same or they should be conserved, the conserved quantity. Okay, so this is A times area times we sometimes call the volume rate of the fluor. Okay, now with that idea we can apply, we can derive formula of Bernoulli's equation. Let's move on. So Bernoulli's equation. Bernoulli's equation. All right. Now let's assume similar condition, but I'll derive formula on how the pressure, density, volume, and the potential energy are interconnected through this fluidic dynamics. Now you have the water pipe runs along the some space, and their size change along the travel distance of fluid. So now they stay in the pipe itself, sitting above the reference ground, so that the middle of input pipe located the Y above ground position or ground plane, and their cross section is A1, and over some given travel time, this fluid actually move delta L1, and the velocity coming across this area cross section is V1, and the pressure applied to this cross section of input pipe is P1. So that amount of fluid as moves along the pipe and then reach out to the output of the pipe. Then output located the Y2 above reference point, and amount of travel distance in given time is delta L2. The velocity coming across this cross section of A2 is B2. So that cross-section area is A2. Okay? The pressure applied to the cross-section of this up is P2. So this amount of volume plug into this water pipe or maybe like some kind of pipe, container pipe, is actually travel along this pipe and reach that output of this pipe, but because of the size of the cross section is changed, the travel distance delta L2 must be changed too, which just changed the velocity V. Okay. So now let's take a look at the potential energy change over this distance. Now, the potential energy of this amount of volume or this amount of mass is what? mg y1, all right? And okay, we got to do this, okay? And then like Let's do this is what at the W1. Let's take a look at just energy, potential energy U1. That is mgy1, and the U2 at the potential energy of, oops, that amount of actually water or fluid actually just move to that the second point two. So that create some amount of potential energy that should mgy2. So if there's a change of the potential energy that create amount of work, so the work created by the variation of potential energy must be U1 minus U2, which means like that is mgy1 minus mgy2. So that takes the mg out of two term, or you can take the minus sign out of that. That should be y2 minus y1. Minus sign right there. And now you want to estimate total amount of work from the motion of this fluid from the position point 1 to the point 2. So that should be the force times travel distance d, and force times travel distance 2, and plus variation of potential energy. So that should be W3. If you plug that, oops, plug the force and the travel, I mean the force times as usual, as you know, Newtonian system, force times displacement is work. So if you apply that, that should be F times F1 times delta L1. And now because of your cross section is negative direction, so that should be F actually 2 times delta L2, and the plus work 3, W3, potential, and the work from the potential energy variation. So that work created by this amount of travel of fluid from this point to that point, or same for the outlet. From here to here is work 2. So like this is work 1, and this is work 2. And that also have this amount of potential variation. So if you plug that F1, the force is function of pressure. That is F1 times area, P1 times actually A1, right? The pressure is force divided by area. So yes. So the force is pressure times area. So that the force exerted on this cross section of this water is the pressure times A1, and F2 is the same, P2 times A2. But now you are looking at the opposite direction. Now this one is pressure inside the fluid, but this pressure is outside of the cross section, right? So that you should add the minus sign to the number 2. So that should be P1 A1 delta L1 plus minus P2 A2 delta L2 plus, now you have actually minus, you have like a potential energy from W3, so that should be mg y2 plus mg y1. So that amount of actually work should be same as the variation of a kinetic energy. Okay, so now you have this amount of work created by the flow of fluid from the input and output. Let me just change the color. So input from here to here, output from there to there, the same amount of energy is created by the variation of kinetic energy too. So that should be 1/2 m1 b, or like a b, oh yeah, so the m actually m2 b2 square minus 1/2 m1 b1 square. Okay, so that is same as this one. So now you apply that the volume, rate of flow. Remember, area times velocity is same as and area times the velocity too. But here, this one is also same as delta L1 over delta T. This one is delta L2 over delta T. So that actually same as A1 times delta L1, A2 times delta L2. And the mass itself is density times A1 times delta L1, which is same as low density times area times delta L2. Okay, so same mass rate. So if you plug that into this formula, so you gotta just rearrange this formula. Then that should be that should be 1/2 low V2 square minus 1/2 density times V1 square equals P1 minus P2 minus low GY2 minus plus low GY1. Okay, so you just rearrange this. So if you put the quantity, physical quantity of pressure and the velocity and the density to the left-hand side with the 1, all the quantity to the left-hand side you move that all the quantity to the left-hand side of the input, and all other quantity of the index 2, the point 2, the output to the right-hand side, and you can rearrange it in terms of their index. So the P1 plus 1/2 low V1 square plus low GY1 is equal to P2 plus 1/2 low V2 square plus low GY2. So the pressure plus the density times velocity squared plus potential energy variation must be conserved, regardless of their location. Okay, wherever you're standing, pressure plus density times velocity plus potential energy variation must be conserved. Okay, this is the Bernoulli equation. So if the speed of a fluid element increases as the elements travel along horizontal, the pipe, the pressure of fluid must decrease and conservatively. So that means you have higher velocity. Some point. Now take a look at this pipe. Because the pipe is shallower toward the end of the pipe, then you have the higher pressure. Speed is the higher, right? And speed is the higher because your cross section is because that change the pressure. So depending on the pressure of the pipe along the cross section, your speed also just determined. So their combination pressure, velocity, and their potential, the height, they're all interconnected. So one of the variables is increased, the other variable goes down, because in that way, that total amount of this physical quantity can be conserved. Okay?
Mhm.
So this is the combination of three variable: pressure, density, and the velocity. So in order to find out, just like kinetic energy, I mean total energy conservation, you can think of this is the fluidic version of energy conservation. So if you know the pressure, and you can drive for, find the value of velocity or vice versa at the different locations, right? So you can look back the derivation of this formula to understand how it's derived, but that's, if you just go step by step, it should make sense, because basically we just apply the Newtonian approach using the energy conservation of this two spot of fluid in the floor. Do you have any question?
No.
Okay, then let's start work on the example problem that will help you to understand more about how this formula actually works. But we're gonna start with the example problems from the beginning of this topic. So let me open up the example problem. Okay, let me, what was the problem? Okay, let me, number one, 13-5. Okay. Let me know if you're not able to actually see it. If you can't see it, just let me know. I'll just replay it.
Example 13-5,
Do you hear it?
elevation effect on atmospheric pressure. Question number 1, A. Determine the variation in pressure in the Earth's atmosphere as a function of height y.
Oh, hold on a second. Let me turn up my because it also already have the hold on. Okay. I may want to just make hold on a second. Share. Give me 1 second. Okay, so I'm gonna share my screen again. So that video file itself already have me in the screen. So all right, let me replay it.
Example 13-5, elevation effect on atmospheric pressure. Question number 1, A. Determine the variation in pressure in the Earth's atmosphere as a function of height y above sea level, assuming G is constant and that the density of the air is proportional to the pressure. This last assumption is not terribly accurate, in part because temperature and other weather effects are important. B. What elevation is the air pressure equal to half the pressure at sea level? So we have to find the relationship in the pressure and density first. So usually the pressure is proportional to the density and density proportional to the pressure. The ratio between the density at different altitude, different height above sea level is also proportional to the ratio between the pressures at those two different heights. So usually the density of the gas, which is air in this problem, is proportional to the pressure. So from that, the ratio between, as I said, the density of gas at different level due to the pressure applied to the gas at different height should be proportional to the pressure ratio of the pressure at different height. So here P naught is atmospheric pressure, which is 1.013 times 10 to the 5 Newton square meter. And the density at sea level should be 1.29 kilogram per cubic meter. So this is the density of the air at sea level. First of all, we know that this pressure, fractional pressure, is a function of the height, which is minus density times the acceleration, gravitational acceleration constant g. So now if you replace density of gas at the height, at the height above sea level, then that should be P times rho naught over P naught times G. So if you if you swap the P and Y from both sides of this equation, then that should be dP over P equals minus rho naught over P naught G dy. So as you can see, this equation is basically given by the integral of the pressure and the height from the sea level all the way to the given height of this problem. So if you integrate it, then left hand side, let me just write it up, the whole equation with the integral. So that is integral of Tp over P from P naught to the P equals minus rho naught over P naught, which are the constant value, times G over integral times the integral of dy height from 0 to the specific height of interest. So we need to actually derive formula out of this integral. Then that should be like the integral of 1 of P in dP should be log function. So that is log P from P naught to the P. So that is log natural log P minus natural log P naught, which is log P over P naught is minus rho over P rho naught over P naught times G y. So now we want to actually express this equation in terms of the density and the pressure at sea level. So pressure P, which is a function of y, is P naught times exponential function minus rho naught z over P naught times y. So as you can see, that pressure is exponentially decay in height y. So y goes higher than pressure of the air is just getting lower. So number B, we got to plug the numbers of condition into this formula. So let's take a look at these coefficients just before variable y. So that is rho naught over P naught times G, right? So that's rho naught from that is 1.29 kilogram per cubic meter. So let me just plug it to 1.29 kilogram per cubic meter times G is 9.8 meter per square second. And the P naught is 1.013 times 10 to the 5 Newton square meter. So if you plug that all the number into the formula, then that should be 1.25 10 to the minus 4 inverse meter. So now the condition is at what elevation is air pressure equal to half of the pressure at sea level. So the pressure itself, the P becomes half of the pressure at the sea level. So that should be 1 of 2. P should be 1 of 2 P naught. So you plug that, then that should be 1 over 2 P naught equals P naught exponential minus rho naught G over P naught times Y. So if you cancel P naught out of the both sides of the equation, then that should be 1 over 2 equals exponential function 1 minus 1.25 and to the minus 4 inverse meter times Y. So now we want to actually find Y out of this formula. From that, Y should be log exponential log 2 over 1.25 times 10 to the minus 4 inverse meter. So that is 5,550 meter. So when you reach the height of the 5,550 meter, that pressure becomes half of the pressure at sea level.
Okay. Do you have any question regarding this problem?
Not right now.
Okay, yeah. So you gotta maybe just take a look back and just follow up on that procedure of derivation. And if you're not familiar with the integral or integration of local function, you can take a look back the calculus, calculus book. There's some sort of like that is very first degree of the integration of local function, so it's straightforward. I can explain that if you not fully understand how to do it, I can just show you how to just drive the formula. So let me know. And let me show you the one more example problem, and then I'll just wrap up the today's session. So
Okay.
yeah, I'm gonna have like maybe 6 or 7 more examples. I'll just maybe show you all those problems in the next section and next Tuesday, next Monday. But next one must be this one. This should be the simpler. Yes, all right. Okay.
Okay. Sample problem 14.03. Balancing of pressure in the U-tube. The U-shaped tube in figure 14-4 contains 2 liquids in the static equilibrium. Water density low W is 998 kilogram per cubic meter is in the right arm, and oil of unknown density low X is in the left. The measurement gives L 135 millimeter and D 12.3 millimeter. What is density of the oil? So now is the pressure in both the liquid is in this U-tube, this U-shaped tube, pretty much balanced in equilibrium. So the P input should be P naught, which is actually the reference pressure, times low W, water, times G. Now here G is acceleration, I mean the gravitational acceleration constant G. This is right arm. Right arm of this tube filled with the water. So the pressure on that side should be expressed with this formula. So now that should be same as the pressure on the left arm, which is filled with oil. That is low, the P naught atmospheric pressure times plus rho x, unknown density of oil times gravitational acceleration constant g plus L plus D. That is left arm. As you can see, that height of oil is about slightly higher than the water with the D, so that you have a little more pressure out of that amount of difference. So now from this formula, you can easily derive the expression of rho x in terms of rho w and L and D. So from that, rho x equals rho w times L over L plus D. Here, L is what? 135 millimeter, and D is what? 12.3 millimeter, and density of water is 998 kilogram cubic meters. So if you plug them all, then 998 times 135 over 135 plus 12.3. So that result of this mass is 915 kilogram cubic meter. That is density of oil in balance with the water and static equilibrium inside of this U-shaped tube.